This is Physical Principles of Quantum Biology, Part 1, Chapter 1, Quantum Theory and the New Observables. For those of you who are new to the subject, I've recently released a monograph with my wife and collaborator Brandy Babcock on the physical principles of quantum biology. The book contains 21 chapters, and these videos will provide lecture material outlining the content of each chapter. You can download the book for free from the Physics Archive. That's archive.org, entry number 2503.11747. So go ahead, check it out. The book begins in Chapter 1 with an overview of quantum mechanics, starting in the year 1900 when Lord Kelvin delivered an address to the Royal Institution outlining two major problems he saw in physics. He described these metaphorically as clouds hanging over the horizon of physics, which he felt obscured the beauty and clearness of the dynamical theory, so to speak. The first cloud was that of the luminiferous ether. Michelson and Morley had performed an experiment that failed to detect Earth's movement through the luminiferous ether, which was believed at the time to carry waves of light. But the inability to detect the so-called ether, which carried light waves, electromagnetic waves, through our universe, posed a problem in terms of the question of what would carry electromagnetic waves if there was no such ether to detect. The second cloud concerns something called the equipartition principle. The Maxwell-Boltzmann equipartition theorem was used to carry out certain calculations in thermodynamics, predict things like the heat capacities of solids. It worked at high temperatures but failed miserably at low temperatures, and the question remained is what was wrong with the equipartition principle, which Kelvin himself did not trust. So these concerns kind of became increasingly important as the years progressed after 1900. Einstein proposed an explanation for the photoelectric effect, and there was a growing understanding that the old classical theory was not going to work to describe a number of emerging phenomena in physics. So prominent chemist Nernst proposed that the leading physicists and some chemists should address this theoretical problem, growing crisis as he called it, and the industrialist Ernst Solvay held a conference in 1911 on radiation and the quanta. Now, the participants in this conference, as you can see in the attached photo, included famous individuals like Einstein, Rutherford, Marie Curie, and you can see Solvay himself in the lower left corner with the Colonel Sanders style mustache and goatee. Now, ultimately, it was resolved as a result of this conference that a new theoretical framework would be needed for a vast reform of the fundamental classical theories of the time. Work on this continued after the conference, and in fact, Solvay conferences were so successful they continue to be held to this day. But throughout the course of the next decade and through until 1925, continuing work was developed on this so-called quantum theory, which in many ways culminated with the development of Heisenberg's quantum mechanics, matrix mechanics, which he published in its earliest form in a paper he wrote in 1925. Heisenberg's key insight, which allowed the development of the old quantum theory, as it was called, into what is now still modern quantum mechanics, his trick was to focus only on observables, things that could conclusively be measured and counted in numbers. He based the new theory entirely on relationships between measurable quantities, and the reason why was because at that time they were trying to figure out the orbit of electrons around the nucleus in an atom. But they couldn't measure the electron traveling in a circular orbit the way we can observe the planets orbiting around the sun. And eventually Heisenberg thought he must dispense with the idea of measurable orbits with well-defined position and momenta entirely. The consequence was the formation of new matrix mechanics, a mathematical approach that was later confirmed to be equivalent to an operator algebra developed by Dirac and, of course, Schrodinger's famous wave mechanics. And this ultimately resulted in a major paradigm shift in the thinking of physicists and certainly the founders of quantum mechanics, who didn't know what to make of it at first, by eliminating references to any unobservable quantities from any physical theories. So what is this quantum theory? Well, the modern framework quantum mechanics today is based primarily on 4 postulates. These are the 4 standard postulates you should see in any standard quantum mechanics textbook, which involve the definition of a quantum state in a mathematical framework. It's known as a Hilbert space. So this quantum state is a vector on a Hilbert space. We can propose a so-called unitary, that is reversible evolution of the state, according to the Schrodinger equation, Schrodinger wave mechanics, of course, and the postulate that observables are all Hermitian. This is a special type of mathematical symmetry that guarantees that the outcomes of any measurements in our mathematical calculus will all be described by real numbers. These are sometimes also known as self-adjoint operators, although there's a technical issue there I won't get into. Finally, the key point is that measurements are probabilistic. We may not be able to know for sure the outcome of a given measurement, but we can predict the probability of those outcomes using a mathematical tool known as Born's rule, Born's probability rule. And this allows us to predict, if not with certainty, not deterministically, the outcomes of measurements. We know with some certainty what the probabilities of certain measurement outcomes should be. Now, this is textbook quantum mechanics. This is everything you need at the most basic levels to do textbook quantum mechanics. But of course, it says nothing about bosons or fermions, symmetrized or so-called anti-symmetrized states. It doesn't give us quantum field theory, and it certainly is in no state to reconcile the theory of quantum mechanics with something like gravity. So even though this is textbook quantum mechanics in its closed form, of course, the theory is only limited to the very specific set of cases that it itself can describe at a textbook kind of level. And as we proceed through the lecture, we're going to see what the limitations of this very well-defined, very accurate, but ultimately limited theory. So here we are. What are the limits of orthodox quantum theory? Well, if Lord Kelvin was around today, I think he would have similar concerns. He might even propose a third cloud hanging over the horizon of physics today. Now, Kelvin was adamant in his view, echoed by quantum theory, that unless you can put a number on your knowledge, then your knowledge is of a meager and unsatisfactory kind. This is kind of a preliminary to Heisenberg's idea that all physical quantities must be observable. And if we can make measurements, we can express those measurements in numbers. So in many ways, Heisenberg's theory was a direct consequence of an idea that Kelvin had proposed the previous century. Now, what is interesting about this is if you look back at the old dialogues between Dirac and Heisenberg, for example, they had their views about what really comprised a theory or what a theory should be composed of. And Dirac felt that theories should be open and subject to revision, whereas Heisenberg thought, no, once you have a theory, it should be closed and complete in the sense that that theory's domain of applicability should be clearly defined. And if there were future discoveries or revolutions in physics, it wouldn't be a modification to the old theory. It would be, in fact, the creation of a whole new theory with a new domain. So they didn't really agree on what a theory should be, open or closed. But one thing they could agree on was that the development of quantum theory should not make use of classical mechanics. And in fact, Heisenberg was adamant that new phenomena require the formation of a new closed theory. So the real issue here, if we now look a little more closely at what is really entailed in quantum mechanics, is that we have this postulate about measurement that requires the existence of a measurement device. And unfortunately for quantum theory or for our conceptualization of quantum theory, the measurement device itself is not described by quantum mechanics, either then in the 1920s or even today. Quantum mechanics fails to describe the measurement apparatus itself, and we have to assume that the apparatus or the experimenters doing the measurement are somehow classical objects, even though, of course, laboratories and apparatus and experimenters are all made of the same atoms, electrons, nuclei, and so forth that we have in our quantum physics experiments themselves. So there's a kind of incompleteness in quantum mechanics due to the fact that we have these beautiful postulates that define the mathematics of quantum theory in this abstract sense. But in order to actually predict results of our calculations, we need to add this classical measuring apparatus in by hand. And this kind of ad hoc addition to the theory has been very troubling to physicists throughout the decades since quantum mechanics was developed. Of course, quantum mechanics still has problems in terms of its relationship to relativity. We have some versions of quantum electrodynamics that are compatible with relativity, but to go to full-blown quantum gravity, of course, this is still a major open project, a grand challenge of physics. And so this measurement problem, this idea that we have a quantum system that evolves unitarily in time, we can predict certain expectation values, certain likely results or average results of the experiments we perform on these quantum systems, all still hinges on the existence of this seemingly classical device that can somehow collapse the wave function, so to speak, to get this probabilistic superposition of possible outcomes narrowed down to a single actual outcome that we observe during any experimental setup. So there's a real divide between the quantum and classical realms. Quantum mechanics and classical physics are in some way incompatible, even though we think, on at least in some limit, one theory should be a special case of the other. Classical phenomena are assumed to emerge from underlying quantum systems as you add more and more atoms and the system gets bigger as you approach the macroscopic limit. And this assumption is known as the correspondence principle, that on some level, quantum phenomena should correspond to macroscopic classical effects. However, quantum mechanics, as I've mentioned, is incomplete without classical theory. We have to assume classical measuring devices in order to carry out our measurement calculus and predict the results of our experiments. So rather than being able to derive classical physics from quantum theory, as the founders of quantum mechanics like Bohr and Heisenberg expected, classical theory is a required prerequisite of quantum mechanics. And this, from a theoretical point of view, is very problematic. If you look at Einstein's relativity, for example, Newtonian physics, Newtonian kinematics, are a special case of Einstein's special relativity in the limit where things move slowly. But the limit where things get big enough that quantum systems become classical has still never actually been formally mathematically defined with any rigor. And so we still have this enormous gap between the quantum and classical, which has not been bridged in anything but a kind of ad hoc speculative sense. Now we know that quantum systems are quantum and classical systems are classical, but where we draw the line is unclear. And in fact, that line drawing step is known as the Heisenberg cut, which in some people's view is completely arbitrary. But we can think of systems that bridge the gap between quantum and classical. Classical systems, according to one estimate by Bassi and co-workers in the Review of Modern Physics, can be trusted. Classical systems we see for objects on the scale of micrograms or larger. Objects as heavy as 10 to the 6 grams or bigger. Whereas quantum effects can be expected to ultimately govern the dynamics of our system for very small objects on the scale of about a zeptogram or less. That's 10 to the power of negative 21 grams. So for a physicist, you can see right away there are 15 orders of magnitude gap between the kinds of systems we can treat as decisively classical and the kind of systems that we should consider unequivocally quantum. And so the question of how to negotiate this quantum classical divide, as I mentioned, is still unanswered. The physicist just does this division in his mind, separating the quantum system under study from the classical laboratory apparatus, the knobs he turns and buttons he presses. And this artificial separation, the Heisenberg cut, so to speak, is good enough for most of our applications when we clearly know in our laboratory the difference between the system we're studying and the seemingly classical apparatus that we use to study it. Now, one of the reasons I became interested in biology was because, of course, biology a priori from first principles has no such artificial boundary. If we look at the scale from zeptograms to micrograms, biological systems, living organisms, have stuff going on at every scale, all the way from individual molecules and things like DNA, genes, ATP, other individual biological molecules, scaling up to macromolecules like proteins, organelles, various components of the cells, and ultimately tissues. Biological complexity exists on every scale. So living systems have seen no need to perform an artificial Heisenberg cut. They literally have things going on all the way down or all the way up if you start from first principles. Now, beginning from first principles, Schrödinger, for example, in the 1940s, claimed that classical physics would be fundamentally inadequate to understand molecular biology and living processes because once you go down to the microscopic scale, statistical fluctuations naturally destroy classical order. And this is interesting, especially because recently, some critics of quantum biology have claimed that decoherence, the same kind of random fluctuation, should destroy quantum mechanical coherence at this scale. But the problem with this argument is it applies just as well to classical order as it does to quantum order. And so the real question is why biological order should exist at all. So Schrödinger really argued forcefully in his claim that the classical physicist's expectation about biology, far from being trivial, is wrong. That we really cannot even hope classical mechanics to explain biology at the molecular level. And we must understand how quantum mechanics preserves this coherence as you scale from the quantum scale all the way up to the classical. Now, similar ideas were developed by another Nobel Prize winner, Szent-Györgyi, who proposed that delocalized common energy levels must be necessary in biological molecules to explain their unique catalytic properties in enzymes, for example. And if you read his paper Toward a New Biochemistry in 1941, he had already proposed that electronic delocalization was very important for certain biological processes. We now know electronic delocalization is critical even for the structure of biomolecules. If you've ever studied organic chemistry or taken a aromatherapy course even, these aromatic molecules, their whole existence and many of their wonderful numerous properties depend on the electronic delocalization of the molecules themselves. Now, this idea that delocalized electrons form common energy bands, like we see in semiconductors, didn't really see formal development until the advent of Marcus theory in the 1950s. Now, Marcus identified how the complexity of electron transfer reactions in chemistry depended on a number of factors, including energy conservation, solvent dynamics, and ultimately, in the decades of work he put in from the 50s to the 80s, so-called non-adiabatic quantum effects. And these non-adiabatic quantum effects that he considered in his 1984 paper on the subject really explained the key role of quantum mechanics in what should otherwise be a simple chemical reaction, just an electron being transferred from one molecule to another. And now we know, in fact, that for the most part, these electron transfer reactions occur as a result of electron tunneling, as Winkler, Gray, and other colleagues conclusively identified biological electron tunneling in cytochrome C in the early 80s, and we now know that electron tunneling is essential for many aspects of cellular respiration and other metabolic chemical reactions in living cells. So my view is that if we approach biology from first principles, we can learn new things not just about biology, but also potentially physics. Now, a lot of work in quantum biology approaches biology from classical assumptions, classical biology, and then proposes to find effects that violate classical physics and, say, give organisms some selective advantage in order to identify possible so-called non-trivial effects, quantum effects in biology. But my view is that even when this approach is used at its best, it's essentially ad hoc because we're imagining a classical haystack, so to speak, and going looking for quantum needles in it. But really, if we really believe quantum mechanics, we should begin with the quantum mechanical postulates first, and then we can explore the full range of possible quantum states and effects at their most microscopic level, at the level of atoms and molecules. And then as we scale up, gradually introduce classical approximations only where necessary and appropriate, rather than assuming our classical approximation first and then working backwards to find out where it's violated. Now, don't get me wrong, both approaches can work, but my view is that the fundamental bottom-up approach, so to speak, will enable biological systems to be investigated in a way that is more realistic, more accurate, and ultimately more systematic for me as a physicist. So again, what are these postulates? Well, actually, they emerge from fundamental principles of nature. Heisenberg famously developed his theory of matrix mechanics beginning in 1925 after he had an epiphany on the island of Heligoland. And he proposed, as he continued his work to the end of the 1920s and published a textbook on it in 1930, three basic principles in light of the correspondence principle. Again, this idea that on some level, things that we observe on the quantum scale must correspond to things that we observe on the classical scale, things like position and momentum and energy. So using the correspondence principle as his guide, he proposed that conservation of energy, as it's expressed in the Rydberg-Ritz combination principle, shown in item number 1 here, the idea that the difference between one energy level and another energy level should be the same as the difference between either of those two energy levels and a third energy level. Now, second, he proposed as a basic principle the quantization of energy. If we want quantum theory, things must be quantized, which simply means that things like energy or angular momentum come in discrete little packets that we can label 1, 2, 3, 4 up onto infinity, the same way we might get single serving packets at the grocery store or on an airplane. But the thing about these single serving packets is that they can't fundamentally be divided into smaller packets. These are the fundamental quanta of nature itself. Now, third, he based his theory on something called the Bohr frequency relation. And this is where, in fact, Max Planck's insight into quantum theory really take hold. This idea that there's a so-called fundamental quantum of action known as H, Planck's constant, and the relationship between the energy contained in a system, or the difference between two energies of the system, the energies of two different states of the system, is proportional to some frequency. And that the relationship between the energy and the frequency is given by a constant of nature, H, known as Planck's constant. So he took these three things, conservation of energy, quantization of energy, and the Bohr frequency relation, which emerged from the quantum of action, and he used the correspondence principle to reason about how a quantum theory of mechanics should look based on what we already know about classical mechanics, Newton's laws and the Hamiltonian principle and such. And from this, he was able to effectively derive quantum mechanics in its textbook form as we still see it today. Now, all of this in the form we see it today depends on this funny property called Hermitian symmetry. So this is a mathematical symmetry, and in some sense the symmetry of nature, that ensures the conservation of probabilities, for example, in our quantum system. That probabilities should always add up to 100%. And if they don't, that means something got lost. But for a closed system, the conservation of probability should be maintained. If I lock something in a safe, if I lock $1,000 in a safe, when I come back, all $1,000 should be there with 100% probability unless I was robbed, right? Now, the mathematical expression for this Hermitian symmetry takes a unique form. If we have a Hermitian operator capital H, then we say it's equal to its Hermitian conjugate, which is shown as superscript dagger attached to the letter. So for something to have Hermitian symmetry, it means that the operator, the Hermitian operator capital H, must equal its conjugate transpose, H dagger. The physical significance of this funny mathematical property is it guarantees that the eigenvalues, the energy states of the system, these discrete packets of energy, are real. They don't take on imaginary values. And that if we use this Hermitian, say Hamiltonian operator, to describe our dynamics, the dynamics will be reversible, that nothing is lost or gained, and we could say play the tape of our dynamics of our system backwards, so to speak. The only thing with this, although it works very well in principle and it makes sense as a fundamental theory, is that when we look at reality, a lot of things aren't reversible. If I crack an egg, I can't put it back together again, as the old children's nursery rhyme says, all the king's horses and all the king's men couldn't put Humpty Dumpty back together again. And so we see an arrow of time in our daily lives that suggests that for many practical purposes, this idea of Hermitian symmetry, time reversal symmetry, actually breaks down. And in fact, we now know that Hermitian symmetry is not as fundamental to quantum mechanics as it was once believed. Although Hermitian symmetry is sufficient to guarantee real eigenvalues and reversible dynamics in systems, it's not necessary. There are now other symmetries that are coming to be understood, such as another kind called parity time symmetry, quantum mechanics. And so what was viewed as being one of the most fundamental symmetries of quantum theory is now becoming understood as not even necessary. So we have this thing called non-Hermitian quantum theory that breaks from traditional quantum theory. And these non-Hermitian systems can often exhibit remarkable properties that I believe in many cases are critical to living processes because, of course, living systems aren't closed systems. They have complex boundary conditions, and things get lost. Things go in and out of living systems all the time. I have to breathe air in and breathe carbon dioxide out all the time to stay alive. So we don't have systems with conserved properties the way we like to think of them in conventional quantum mechanics. Now, there are also phenomena called resonances that emerge in non-Hermitian open quantum systems theory, which have a lot of significance in physics and potentially great significance in biology as well. Certainly in chemistry, resonances play a key role in our understanding of many molecular bonds and so forth. Now, another interesting thing is the potential for directional transport in a non-Hermitian theory. So in a Hermitian dynamical theory, all the dynamics are always reversible. But what we really want to see if we study living things is directed transport, where we have things go forward, but they can't go backward. I grow up, but I can't unage myself. And so this so-called non-reciprocity enables us to define energy flow in preferred directions and ultimately even the flow of time in the forward direction. Now, finally, open quantum systems exhibit complex or incomplete spectra due to coupling with the environment, which make them very different from our usual study of Hermitian systems, which are complete always in the formal sense that Heisenberg, for example, considered necessary in order to describe a mechanical system authoritatively. So how could we make a complete theory of non-Hermitian quantum theory? This is an open question, and in many ways, non-Hermitian quantum mechanics can be simplified to Hermitian quantum theory through pseudo-Hermitian operators and the like, but that's a bit beyond the scope of this video today. Open quantum systems theory for biological sciences, I think, will be very helpful because unlike isolated quantum systems, living organisms must continually interact with their surroundings to survive. And now, paradoxically, this environmental coupling preserves the quantum effects that are essential to sustain life. That I have to eat and I have to breathe oxygen in order for the respiratory chain in my cells and my mitochondria to keep going. And if I stop breathing or I stop eating or even drinking water for long enough, I will die. And these quantum mechanical processes like electron transfer that enables respiration and other catalytic reactions that enable metabolism will stop. So really, we almost need to turn our picture of quantum theory on its head in order to understand how environmental coupling actually preserves the fundamental quantum effects that have been established in biology since the 80s, if not earlier. Environmental coupling is necessary to maintain continual energy and information exchange with their surroundings. And the quantum coherence that's necessary for electron tunneling reactions and for other certain preparation of catalytic states. Biology has to find a way to preserve these things rather than destroying them. And biological systems really need to work on the right timescales in order to carry out certain reactions or electron transfer steps that are just the right speed so that they're coherent enough for the reaction to occur, but shall we say decoherent enough for it to be directed, not time reversible. This is all necessary to maintain order in biological systems and sustain the complexity of living systems. And if you haven't hinted from what I'm suggesting so far, this is all essential to maintaining a kind of thermodynamic flow, that the non-equilibrium properties of biology, of course, I'm not completely at rest, even if I have a constant regulated body temperature. I'm also constantly producing heat that's dissipated to my environment. And Schrödinger himself thought that the role of free energy, or as he called it in his 1944 book, What is Life? Negentropy, is really the essential characteristic to understanding living systems. Now, there's a lot of quantum mechanical models that are already used to study molecular biology. These systems, even on the molecular scale, can already be extraordinarily complex when we consider electronic states. If we look at the simulation methods that are already being used, we begin with the Born-Oppenheimer approximation, which says that the nuclei and the electron orbiting around them, so to speak, can be considered separately. That the nuclei can be considered essentially classically as classical point particles, and the electrons can be considered as a kind of density, a uniform density or perhaps a variable density around the nuclear state. But once we've solved for the electronic properties of the system around these seemingly classical nuclei, we can get all the properties out of the system. And this kind of picture of molecular biology, or really even simply chemistry, is the cornerstone for approximation methods like density functional theory and Hartree-Fock theory, where we include only simple quantum exchange effects due to the fermiotic nature of the electrons. Now, as things get more complicated, if we have an electron undergoing a quantum jump tunneling from one molecule to another, we might need to take what's called a multi-configuration approach, where we need to consider different electronic configurations of the system that are only weakly coupled, for example, in a tunneling effect. And we might address this through perturbation methods, which can get very complicated very quickly. Now, if we fail to satisfy the Born-Oppenheimer approximation, we get into something called non-adiabatic quantum mechanics and quantum dynamics. And in this case, we really are going to rely on multi-reference, multi-configuration theories and even what are called coupled cluster methods, where we begin to really consider the full complexity of the quantum mechanical system in question. And now, if the quantum mechanical system is too complex to study the whole system at its full level of complexity, we might use what's called a quantum embedding approach, where we find certain mathematical approximations in order to embed the full complexity of our quantum system of interest in its surroundings, the surrounding solvent and protein, where a classical or semi-classical approximation might be appropriate. Now, this can cover a lot of effects, but it may not account for all of the dynamical effects due to interactions with the environment. And dynamical mean field theories are often used now in order to account for certain more complex aspects of the system before going to full-scale non-Hermitian quantum or Green's function method, which allows us to consider the full nature of the interaction of a system of interest with its quantum mechanical surroundings as well. So quantum mechanical modeling can be very complex for these systems, and highly advanced methods have been developed for physics and chemistry simulations of this kind. So right away, if you're doing complex quantum mechanical calculations, you may need a high-performance computing architecture, a supercomputer, if you will, in order to do these large-scale simulations and matrix diagonalizations to get our energies, our eigenvalues. Now, often classical approximations can be good stand-ins for quantum effects if we really understand the nature of the quantum effect we're studying. But we don't always know the correct classical parameters to use to develop our simplified classical approximations. So sometimes we can predict the parameters in our semi-classical theory from first principles, but other times we don't know what they are, or they're too complex to calculate. And so machine learning methods have been used to find hidden symmetries of quantum mechanical problems in the hope of parameterizing effective classical potentials to treat otherwise quantum mechanical systems. Now, where these kind of semi-classical or quantum mechanical approaches using classical computers fail, it's now being proposed that quantum computers may truly be necessary to address the computational complexity of studying things at the molecular scale in chemistry, materials, and of course biology. Some of the challenges for quantum biology as a quantum theory of biology are, first of all, the self-interactions that exist in biological systems. Homeostasis, the ability to self-regulate, is a key feature of all biological systems, but this kind of self-interaction has always been at odds with the linear nature of textbook quantum mechanics. Now, we have the measurement problem, or perhaps I should say we don't have the measurement problem for living organisms because they don't have any classical measuring apparatus embedded in them. Living organisms, in the most simple simple way, don't go into laboratories and assume they have apparatus that are classical to study quantum mechanical effects. So, in one way, we've simply absolved ourselves of the so-called measurement problem of quantum mechanics. But on the other hand, we really have to figure out how classical approximations emerge in biological systems if there's no a priori measurement devices to reduce things to classicality, so to speak. And of course, the final problem is the enormous complexity of biological systems. Even classical biology is enormously complex. And these quantum effects are now embedded not in a sterilized laboratory environment, but a rich thermal environment that can't be treated as completely being at equilibrium either. So there's a lot of very interesting fundamental challenges that we face studying biological systems from quantum mechanical first principles. And I believe that this kind of study can lead us to discovery, even potentially, of new fundamental physics. People like Schrödinger and Niels Bohr believed that new fundamental physics would come out of biology. And I, too, believe that emerging discoveries may challenge the current scientific understanding of physics as well as biology. So this vast reform of concepts that was originally proposed by Nernst when he called the first Solvay conference in 1911, continues today as we hope to bridge the gap between quantum classical worlds, and as we consider things like resonances and singularities, which are fundamental to physics, but sometimes challenging to describe mathematically in a linear theory like quantum mechanics. And my hope is, as we gain greater insight and knowledge into these things, that new physical principles may emerge to help us, ultimately, for example, to quantify the meaning of the correspondence principle, as well as other governing principles in physics. So what does the future of research in quantum biology look like? As I mentioned, I hope we may discover undiscovered biological and physical phenomena. We have hopes of developing quantum biotechnology that may use biomimetic effects to enable sophisticated bioengineering and medical engineering. My hope is that advanced biomedical applications will also emerge from quantum biology. The work we consider today may have significant implications for things like molecular electronics and even biological computing, as well as potentially revolutionary applications in material and energy science. If we can understand some fundamental properties of enzymes which carry out reactions at terrestrial temperatures that we ourselves as human technologists need to perform at high temperatures and pressures, we may be able to produce revolutionary applications with great industrial and commercial consequences. So please, if you've enjoyed today's lecture, check out Physical Principles of Quantum Biology. You can download it from this website. Find the abstract and find the book, download it. If you're a researcher, a student, or just curious to venture beyond classical biological explanations. And finally, in conclusion, if you have any questions, don't hesitate to reach out. Again, I'm Dr. B. This is my email address, nbabcock@gmail.com. You can check out other YouTube videos on my YouTube channel at Dr. Babcock. And an enormous thanks go out to my wife, Brandy Babcock, and collaborator on the book, Physical Principles of Quantum Biology, and on the development of this slideshow today. So thanks to you all finally for watching, and have an excellent day. Cheers.